So we're still in the review stages. So last week we reviewed just quantum mechanics, quantum harmonic oscillator, simple and forced. And now we're going to do a review on classical field theory. Okay, CFT, classical field theory. As I said, it's just reviewing. This is stuff that I assume you know-ish. Okay? And just to set the notation and just to remind you of a few things, and use things that we're going to use later on when we do a QFT. By no means is meant to be a thorough review at all. Okay? So the first thing is, we're going to start with the space-time. Okay, so a space-time consists of a pair which is a manifold and a right symmetric. So this is a general coarse space-time. Does anyone here not know what a space-time is? Okay, so good. If somebody doesn't know, do go back to the books and refresh your memory. Okay, I'm not going to go through basic GR stuff, but I'm going to go through some GR stuff that we're going to need later on. So this Lorentzian metric, this means the signature is n minus 2, where n is the dimension of the manifold. Okay, essentially in 4D, this means you minus plus plus plus. Okay, you diagonalize the metric in terms of elements which are minus 1, plus 1, and 0. You sum up those elements in the diagonal, and that gives you the signature. Okay, and we're going to choose of a Riemannian metric, a Riemannian connection, sorry. So this means, in particular, so a Riemannian connection, that's what we call the Christoffel symbols. Riemannian means that it's symmetric, and it also means that the covariant derivative of the metric is 0. Okay, so this is your covariant derivative that you can get in terms of the Riemannian connection. Okay, so I'm assuming this is stuff that you know. And now we're just going to look at the action of different fields. So consider a field phi. So this denotes any type of field. Okay? This is any field. I mean, this can be a scalar field, this can be a spin 1, spin 2, whatever, even in general can be self-interacting as well. Okay, and then you have your action functional it's a functional because it's a function of phi, which is a function of the space-time point. So x obviously is a point in the manifold. And this is an integral over some region. This omega is a region of space-time, and L, this curly L, is your Lagrangian density. Okay, so a couple of things about this. First of all, in here, there's a square root of g hidden. So I will give a couple of explicit examples now, but your covariance is coming in from the square root of g, which is inbuilt in the L. Okay, some books use the notation where the square root of g is already the Lagrangian density. Some books use the notation where the square root of g is outside it. Another thing is, I'm considering here just first order derivatives of the field. Okay, That's in general not true, but in most of the field theories that we're dealing with, that is the case. So from this, you use your action principle, which tells you that under a certain variation of the field, your action is extremized. So you want to extremize the action under a variation of your fields. This phi is a say can denote any fields, and you can have various fields in your physical system. And we're going to impose also that the variation of the fields on the boundary of your region omega is 0. So this gives you the Aula Lagrange equations, or EOM just means equations of motion for the field phi. So you look at the functional derivative, and that has to be 0. So you can derive this. So I'm not going to. You can find this in books that the functional derivative is given by the partial derivative of the Lagrangian density with respect to phi, and then this other term here. Okay, so you can exercise if you wish, or you just can look it up in books. This very standard derivation. For this to be 0, this is your action principle. Okay, this comes because this functional derivative, and the definition of functional derivative is if you take the variation of the action, then the integral here is your definition of functional derivative. So this is you look at the change of the integrand, the change in the Lagrangian density due to the change in the fields. So this equal to 0 is the Euler Lagrangian difference. I'm assuming you've seen this, but you won't need to use it explicitly in the course anyway. Any questions about this? This is quite standard so far. So let's look at a couple of interesting examples. One of them is the case of the scalar field. The scalar field is really the field that we're going to be using from now on until the end of the course, so this is a very important example. So this is a free scalar field. We're going to give a mass to it for now. Later on, we're going to set the mass to equal to 0. By free, what we mean is that the equations of motion for the field are linear. Okay, so the equations of motion are linear. So equations of motion, I'm using distinctively the term equations of motion for the field, or the field equations. Let's call it the field equations. Okay, so in this case, so as I say here, phi denoted any field. It could be tensorial field, not just a scalar field. In this specific example now, phi is a scalar field. Okay, and this is the action corresponding to the scalar field. Okay, so as I say, so this is your Lagrangian density curly L that I just defined. As I was saying to you, I'm including the square root of the determinant, so G is the determinant of the metric. So I'm including the square root of that in here, so you have a covariant volume element. And then this is your kinetic energy term in quotes, and your potential energy term, which contains M is the mass of the field, R is the Ricci scalar, and psi is just a coupling constant. Okay, it couples. It's a coefficient a coefficient of the coupling between the scalar field phi and the Ricci scalar, which really has the gravitational field, the second order derivatives of the gravitational field.
Yes, the G mu is a background field, right?
Is the what?
It's a background field, or does it have dynamics?
I haven't really got into that yet.
Okay.
I haven't got into that. So in QFT, in core space time, it's going to be a background metric. And here I'm using units c equals 1 and h bar equals 1. Okay, speed of light and Planck constant are equal to 1. Otherwise, you have to, just cease jumping around here. So now you can derive the equation of motion for the field. So you can calculate this, and that gives you the so-called Klein-Gordon equation. Okay, so this is or if you wish, it's the curved space-time version of the Klein-Gordon equation. So this guy here is sometimes it's denoted by box, and this is just, it's called the down version. And obviously it's a covariant derivative, and so it contains the metric comes in here. As I say, this is for free scalar field. What that means is that this PE is linear in the field phi. If you could have higher order polynomials in here, and that would give you a field equation which is not linear in the field, a self-interacting field. So we're not going to be dealing with that sort of scalar fields. Okay, so this is an important equation we'll be looking at throughout the course. Any questions? Has anyone not seen this? Alguém não tem visto isso? Has everyone seen this Klein-Gordon equation? Apart from Alex. Okay, so this is the scalar field, very important. Another one is gravitational field. Okay, the metric. So in this case, we have so consider gravitational fields, by which I mean the metric. So in this case, the action functional is the Einstein-Hilbert action. of general relativity. So it's a functional of the field, which in itself is a function of the space-time point. So in here, throughout the course, we're going to have these units. Just for the sake of GR, just a little in honor of GR, just for this little bit, I'm going to reintroduce the units. I'm going to reintroduce C and G. And later on, we'll get rid of them then. So, Einstein-Hilbert action, C cubed. I'm doing this just in 4 dimensions, it doesn't really matter. Okay, so lambda here is the cosmological constant. Which is very small but not here. How many derivatives of the field have we got of this Lagrangian? So what's the order of the highest order of the derivatives that we have in this Lagrangian? 2. Okay, this R, the Ricci scalar, contains second order derivatives, up to second order derivatives in the metric. Now you can rewrite this in a way that it only contains first order derivatives. In that case, however, it's written in terms of Christoffel symbols, and it's not a scalar density. It's not a scalar quantity. Okay? But you can do that. You can rewrite it in terms of first order derivatives. So in this case, I say this because I've derived the other Lagrange equation whenever you only have up to first order derivatives. So it wouldn't readily be applied onto this. Oh, by the way, so another important thing, I don't want to get this too messy. I'm going to ignore boundary intervals. Okay? Or in other words, or if you wish, you can say that the variation of the metric and really the derivatives of the metric is 0 on the boundary. Okay. Otherwise, you don't have to do this. You can not impose that. In that case, you have to introduce other terms in your action to compensate for that. So the equations of motion, you want to take the functional derivative of the Einstein-Hilbert action, and you get. So again, you can look this up. In many books, this is a lot lengthier and arduous than the one for the scalar field. But what you get is this. Now, we've used here a little trick, which is Gauss law. Okay, that's used heavily throughout this sort of calculations. You rewrite your volume integral for volume integral in terms of a boundary integral. So Gauss' law tells you this. Semicolon obviously means covariant derivative, okay? This is standard notation. Semicolon in here denotes covariant derivative with respect to x nu. So same thing here, covariant derivative. And this is an integral over a boundary, the boundary of omega, like this. And this is the surface element and this is square root of minus h. So if we started off with a 4-dimensional volume, and this is a boundary of the fourth dimensional volume, therefore there's a three-dimensional region. And this is, H is just the induced metric on that boundary. So this is the partial metric on the boundary of omega. And this guy here is the oriented element of the three volume. On the boundary. So we're going to see explicit example of this later on in the course. The point is that whenever you have that, so A alpha is just a vector field, an arbitrary vector field, the component of an arbitrary vector field. The point is, whenever you've got the divergence there, if you've got this alpha, you also have the square root of minus g, you get you can do this.
Okay.
Yes.
For little h partial metric.
Yeah, or the induced metric. It's just a induced metric. Now, because we're asking for the variations of the field, in this case the variations of the metric, to be 0 on the boundary of your region, then whenever you get a divergence, you can just get rid of it. A divergence with the square root of minus g. Do not forget this in coarse space then. Okay, so this was used here, and this is used heavily in all these sort of calculations. This tensor here is the so-called Einstein tensor. And it's called G mu nu. Now, we want this to be equal to 0, and so that would be your Einstein equations in vacuum. Okay, this is the case where the only field that you have is the gravitational field. You have no other fields, you have no matter fields. Any questions? Okay, so let's assume that you have some matter. So in the presence of matter, your total action, if the Einstein-Hilbert action plus action for matter, whatever the matter field is, and so you have to extremize this action functional, and so what you get, extremizing this total action gives you, well, extremizing the Einstein-Hilbert action gives you this bit, G mu nu plus lambda G mu nu, and then you also get a term which is the functional derivative of the matter field with respect to your matter field. With respect to G mu nu, we're extremizing this under, so this is under a variation of G mu nu. Okay, in here we're only varying G mu nu. If you vary the field, the non-gravitational field, you get what we did earlier on for the scalar field, for example. If you vary G mu nu, you're going to get variation of this has to be equal to 0, so it's going to be minus the inverse of this factor here. So that's minus 16 pi g c cubed square root of g square root. Now, this is in fact what we call the stress energy tensor. So this is T medium. Okay, so T medium is the stress energy tensor. Acronym SET. Is for the matter field. Whatever the matter field is, it can be whatever you want to put in.
For C to the 4.
Sorry?
It's C to the 4.
C to the 4. Controversial. Why do I have C to the 3 then? Is it not C? Is it not C to the 3 here? Let me put a question. I have C to the 3, so that's why I'm a bit reluctant to concede, but I'll check this. Yes, it should be C to the 4. So where's the C to the 4 come from? Unless the definition of the stress unit tensor is a C factor. But yes, I think that should be C to the 4. So let me check. I'm going to check this. Let me give you just a feel for what the stress energy tensor. So it represents total content of energy and momentum of matter. So if we look at the components with respect to some frame X alpha. So as I say, matter can be anything. It can be particles, it can be a fluid, it can be a scalar field, can be an electromagnetic field. Whatever your favorite matter is. Your caipirinha goes in here. If you take out the gravitational field of it. Okay, so the different components. T00 is the energy density. T0, right? So the standard notation is that mu, Greek indices, like mu, and so on, goes from 0 to the whole, cover the whole space-time dimensions. and Latin indices I, J, and so on, they just take the spatial part. Okay, 0 denotes your time component. So when I say T0I in here, I just mean the spatial components. The time component and the spatial component here, I mean the two time components. So this flux of energy across a surface of constant xi. I0 is the density of the I component of momentum pi, and Tij is the flux of that momentum, that component momentum pi, across a surface of constant action. So in some sense, it's the stress. And just by looking at the physical quantities that these components, T0I and Ti0 represent, you can immediately infer that T0I is equal to Ti0. Okay, T0 is obviously T0. So it can be shown that T mu is symmetric, is equal to T mu, and this is just purely on physical grounds. Now that's important because if you go back to the Einstein, so these are the Einstein field equations. These are the classical Einstein field equations. If you go back here, the metric is symmetric, and the Einstein tensor is symmetric as well. So your left-hand side is symmetric, so you want your right-hand side, if it is the source of the Einstein equations, if it is meant to source a gravitational field within general relativity, you want that to be symmetric as well. Okay, so this is consistent with Einstein field equations. Any questions? Just a few notes on this. Number one, the Einstein field equations are the only possible second order equations, containing second order derivatives in the gravitational field in the metric for G mu nu that are covariant. So that are invariant under coordinate transformations. This was shown by Lovelock in 1969. You could change, yes, in 4D. In 4D, okay. Thank you. You could change your action and include higher order terms, but that's not going to give you second order equations for G mu, that's going to give you higher order equations. We will see how quantum field theory allows you, if not almost encourages you, to have higher order terms. Okay? So it's important to know that. So higher order derivative terms. So R squared, things like R mu, and so on, could be included at the expense of having a higher order field equations for mu. Of having, well, you need other factors, you need coefficients for those terms, and so you will add other constants, dimensionful constants. So at the expense of introducing dimensionful constants, so QFT allows you to renormalize those constants. We'll see these later on. And as I say, having higher than second order equations for G mu. So we'll see that QFT allows, we'll see exactly what I mean by this, for such higher order terms. Okay, so I've talked about coordinate transformations. So this is another, I'm going to make another point, another note. So, first of all, a coordinate transformation is a diffeomorphism from n to n. In fact, if there is two manifolds that, if you have a diffeomorphism between two manifolds, you can effectively say that those two manifolds are equivalent. So by diffeomorphism, I mean a map. This is a smooth C-infinity map from n to n, which is bijective. And such that the inverse is smooth as well. So now, in the previous, when we derived the Einstein field equations from the variation of the action under a variation of the gravitational field of the metric, these were for general variations of the metric. Now we're going to do this specifically for infinitesimal coordinate transformations. So the variation of the Einstein field of action earlier was for general transformations, variations of the metric. So we consider here a specific case due to infinitesimal coordinate transformations. Okay, so in here, you change x mu to x. Some people put the prime after the index. Some people put the prime on the index, some people put the prime on the point. Usually I put it on the index, but for this derivation I'm going to put it on the point. It's more clear to do it like this. This is for some vector field psi. And it's small in the sense that the magnitude of the components is much more than x mu. Okay, so how does it vary? How does the metric vary under infinitesimal coordinate transformations? So the metric is a function of the space-time point, and so we know how it varies. So it's a tensor. We know what the tensorial transformation is under a coordinate transformation. That should be given by this. Indeed, this is what defines a tensor, that it changes in this way under coordinate transformations. So these derivatives are trivial for this particular case of infinitesimal coordinate transformations. The derivative with respect to the first one is just a delta Kronecker. It's equal to 1 if you differentiate with to x mu. It's equal to 0 if it's not the muth component. And the other one, you just take the partial derivative. So this is delta alpha gamma. And then we're doing this to linear order in psi. So we're ignoring higher order terms. This is just because it's a tensorial transformation. Okay. At the same time, you can just do a Taylor series expansion of this. So you've got g prime alpha beta x prime mu, and that is just equal to this. And now you can do a Taylor series expansion here. TS, Taylor series. And again, we just do it to linear order, up to linear order in psi. And again, at I can expand this to linear ordering time. Like this. And now you can equate the two things, and that tells you approximate sign, because I'm ignoring now the higher order terms. So this guy comes from here, and these two terms are the ones that you had originally up here. You can show that all these xi-dependent terms can be written in terms of partial derivatives. Covariant derivatives in like this. So you can try this out as an exercise. The Christoffel symbols in here you include covariant derivatives will include Christoffel symbols, and they're cancelled out between the two terms in such a way that you just get this partial derivatives. Okay, so we now get what we want. We have that the metric tensor transforms in this way, where the variation is given by this, and this in fact is the so-called Lie derivative of the metric alongside. Lie derivative. Okay, so this is the way the metric transforms under infinitesimal Gaussian transformations. So that's an important result. Any questions about this? I should say I don't really want to get in depth about this, but whenever I was doing this, there's something that really puzzled me, which is you're really changing the point here from x mu to x mu plus xi, you're changing the point. So this is an active viewpoint. In here, typically when we do conformal coordinate transformation, in fact, the name coordinate transformation usually means it's a passive viewpoint, that you actually have the same point here and here. But there is another way to look at the coordinate transformation, which is via the diffeomorphism that I said earlier on. Okay, so diffeomorphism would take you from the manifold to the manifold, and you go from a point P to another point phi P. So you're really changing the point. This is the active viewpoint. And this is really what we're doing here. We're really looking at two different points on your manifold. Okay, so the two equations are consistent. And they're equivalent. So philosophically, the active viewpoint and the passive viewpoint are very different. But in practice, for any practical calculations, they're equivalent. Okay, so we want to look at the variation of the action, of the Einstein-Hilbert action under infinitesimal coordinate transformations. We've just seen how the metric varies under an infinitesimal coordinate transformation. You still want to see how the action varies. So we're asking for the action the variation of the action to be 0, to extremize it. So we have the functional derivative of the action, and we saw earlier what this is equal to. There's some funny factor, modular factor, factor of c. So I'm not unsure whether c cubed or c to the 4. Certainly in the Einstein equation, there's c to the 4. In here, I'm unsure. So lambda g alpha beta square root of g. Okay, and this variation, so this is with the upper indices, in here it's with the lower indices. In order to get the variation in the covariant version from the variation of the metric in its contravariant version, all you want to impose is that G alpha beta covariant is the inverse of this guy here. So you do that and you just get that it's equal to this with a minus signs. So this is just minus xi and covariant indices, of course. Alpha beta minus xi beta alpha. Okay, you can derive this as an exercise by imposing that the covariant version is the inverse of this. Okay, and then you also use the symmetry of the tensors, of the metric and the Einstein tensor. And you get, so this is symmetric, and so is this. So you're going to get twice this amount. So this is going to be minus. So the minus is coming from the x's, and the 2 is coming from the fact that these two are symmetric. So this is going to be 2 minus 2c cubed 16 ig. And now square root of g. Okay, so I only have one term with psi, not 2 terms, which gives me the factor of 2. And as usual, we ask for xi to be equal to 0 at the boundary. You do integration by parts, and also you apply Gauss law. Let's do it explicitly for, this is a very standard trick that you use over and over again, so let's do it just one extra step. So star, I'm going to continue this equation up here. Let's continue it right here. So this gives you, well, I can get rid of the coefficient in front of it. So I want to do integration by parts. So I'm going to take the covariant derivative of the whole shebang. Okay, so I want to take the covariant derivative of all of this, because now I can apply Gauss law and I get a boundary term which is 0 if I ask for psi to be equal to 0 at the boundary. But of course I still have to, I've added an extra thing here. Okay, I only have the covariant derivative of psi, I don't have the covariant derivative of the first term, so I have to subtract that. Okay, so this is just an identity. So we just apply Gauss law and the fact, or you ask for psi to be equal to 0 at the boundary. And so that effectively gets rid of this term here. Now, remember the covariant derivative of the metric is equal to 0, so G alpha beta is equal to 0, and so this is just equal to G alpha beta covariant derivative with beta. This must be true for all psi's, and so this tells you that the integrand must be 0. So G alpha beta divergence is equal to 0. So this is the contractant by Yankee identities. So this follows from the invariance of the Einstein-Hilbert action under infinitesimal coordinate transformations. Okay, I did not use the Einstein field equations here. This is just really purely geometrical, so that Bianchi identities are just purely geometrical. Okay. This has nothing to do with the Einstein field equations. How many equations have we got here?
4.
Sorry, 4. 4 equations. How many independent equations have we got in the Einstein field equations?
10.
Why 10?
Because you have symmetric tests.
That's right. So if you didn't have symmetry, you would have two components, two indices, alpha and beta. 4 times 4 is 16, but they are symmetric, and so you have just 10 independent ones. Now, they're not fully independent because you still need to impose the Bianchi identities. So you really have 10 minus 4 really independent components in the metric. So this is 4 equations. In the Einstein field equations, you've got 10 equations. Okay, that's 16. Well, that's 10 equations due to the symmetry of the metric. So the total number of independent components is 6, and this corresponds to the degrees of freedom of GR, to the gauge freedom of GR. Corresponds to the fact that there exists 4 degrees of freedom to make coordinate transformations so the metric, or 2 metrics, or different metrics, which are related via a coordinate transformation, are equivalent, or define the same space-time. They're physically equivalent. Okay, this is, people call it the gauge freedom. Of general relativity. You're free to change the coordinates freely. Any questions? Okay, this is the variation of the Einstein-Hilbert action under infinitesimal coordinate transformations. You can do that also for the matter field. So let's do that now for the matter field. For the right-hand side, for the right-hand side of the Einstein equations. So that's another. I said nodes, and then this is the 3rd node or 4th node that I'm giving. So this is another point or another node. So doing similar for the matter action. Sn. So it's exactly what I just said. So we take an infinitesimal coordinate transformation so we know we've just derived how the metric changes, how the metric varies under such transformation. And suppose that the field varies. We don't know how the field varies, but let's suppose it varies by whatever, by a term given by delta phi. And we assume that the matter Lagrangian is a scalar. By scalar, I mean invariant under coordinate transformations. Okay. We're just applying a coordinate transformation, an infinitesimal coordinate transformation, and I'm assuming that the matter action is invariant. So what that means is this. We assume that the Lagrangian is invariant, and therefore the matter action is invariant. Can you think of a Lagrangian which is not a scalar? That would mean that it does vary under coordinate transformations. So what quantity have we looked at today that does vary under coordinate transformations? Sorry, what I mean is, let me rephrase this. What quantity does not transform like a tensor under coordinate transformations? That was the right question. The connection. Okay, gamma is not a tensor. It has indices, but they're not tensorial indices. So anything that you can construct something which does not have indices from this. You can do this and then beta G mu alpha. Okay. In here, there's all the indices are contracted. This does not have any free indices. But this object will change under a coordinate transformation. Okay, so that wouldn't be that's not a scalar. Okay, so in here we'll just do the variation of this. So we vary. Well, what we mean by this is G. So this is a function of two things: the phi and the gravitational field. Okay. So this is subtraction of the matter action after doing this variation and the matter action before doing this variation. Okay, so this is remember, what we're varying now, every time we're varying different things. Before, at some stage we varied phi, at some stage we varied g. Now we're doing a coordinate transformation. That leads to a variation of both g and phi. Okay, so we have to vary both of them. So we have to vary the Lagrangian with respect to phi, and we have to vary the Lagrangian with respect to g. What is this equal to? Zero. If a teacher asked you what is this equal to, the chances of zeros are pretty high. If it were equal to 3.256, likely the professor can ask you. Okay, so this is zero if phi satisfies the Einstein field equation, the equations of motion. Okay, so I'm assuming that phi satisfies the equations of motion. That was how we derived the equations of motion, by extremizing the matter action with respect to variations of the field. What is this one equal to? Sorry?
T mu nu.
T mu nu. Times a factor that there might be a C or not. So this is the strength energy tensor. And we've seen how this varies. Okay, this varies in this way. Okay. Okay, so this is this is equal to this. Again, this is symmetric. This psi factor is symmetric. T alpha beta, we saw that it's symmetric as well. And so you can compactify this, you can sum them. And now you do, so this is covariant derivative with respect to beta. And now we use the usual thing. You do integration by parts. And so this just gives you all these tricks allowing you to change what factor in the integral you apply the covariant derivatives to. And always you have to have the factor square root of g in coarse space-time. Again, this is true for all xi's, and so this tells you that this guy must be 0. And so this tells you that the stress energy tensor is conserved. So this tells that matter stress energy tensor is conserved if the matter Lagrangian is a scalar and phi satisfies the equations of motion, field equations. Any questions? So this is obviously consistent again. With the Einstein field equations, because we've seen that the left-hand side also, the covariant derivative of the left-hand side is also 0. The contracted by Yankee identities. Okay, we're very close to finishing classical field theory. Just that one last bit is, we're going to deal a lot, when we do QFT, we're going to deal a lot with the scalar field. And there's a couple of interesting features in the stress energy tensor for the scalar field. So let's look at the scalar field more in particular. So one can calculate the stress energy tensor for a real scalar field with coupling constant xi and mass m via the definition of the stress energy tensor that we gave. And that's a mess. So I'm not going to drive the mess, but I'm going to give the mess. Because it's a usefulness. That's a mess. Yeah.
The broken constant psi is dimensionless.
Yes, I think so. So in here I've already set h bar and c equal to 1.
So there should be powers of h bar and c.
Powers of h bar. So there's definitely h bars here. In the mass term there's a h bar.
And psi could be a dimension full constant built out of h bar c.
I really think it's dimensionless. I think I've got this somewhere. I'm not sure. I really think it's dimensional, so I can't. I'm not totally sure. There's a funny thing here. What is funny? Funny in English also means curious. It's not so much ha ha ha, but curious. If you look at the Einstein-Hilbert action, if you look at the Lagrangian, sorry, not the Einstein, but if you look at the Lagrangian that we started out with for this field, we had psi r phi squared. That's where psi appeared. So that if you're in flat space-time, the Riemann tensor is 0, and so the Ricci scalar is 0, and so you would have no coupling. If you're in flat space-time here, so if Ricci tensor is 0 and Ricci scalar is 0, you still have psi dependence. That just comes from the fact that you've taken the derivative. You can't set psi to 0 and then take the derivative. You have to take the derivative and afterwards set psi to 0. So note that even in flat space-time, the transient potential depends
space-time could be curved. If one will know that the concept of Ricci scalar, one could not derive the correct plus energy tensor in flat space-time.
So, again?
Let's imagine you only know about flat space-time. You don't know about curved space-time. You don't know there's such a thing as a non-zero Ricci scalar. How could you possibly derive the correct stress energy tensor in flat space-time for a scalar field? So you wouldn't know about that coupling, that the coupling is there in flat space-time.
Well,
So this is there was some sort of discontinuous limit somehow. So if someone studies the scalar field in flat space-time, they're not going to get this stress energy tensor. If they don't know that space-time could be curved. So we wouldn't have a notion of coupling to
I mean,
curvature.
it's just a bit funny, right? Because if you have a matter, if you have a matter field, if you have a scalar field, you wouldn't really have flat space. So it's only when you have it as a background space. It's only when the flat space was background space that it would make sense to put phi in it.
Well, I don't agree. I mean, people studied electromagnetism in flat space-time
Yeah.
before GR came out. And maybe things were not formulated in terms of energy momentum tensor, but it could have been. If you neglect the action of the fields on space-time.
Yeah, so it's not an exact.
But it's still a large part of physics in many ways. All of quantum field theory in flat space-time is, in that same sense, not strictly speaking correct because the fields you're looking at are actually curving space-time still. You neglect that.
Yeah, so what I'm saying is I suppose it's the neglecting, so that's what bothers me, it's neglecting that makes, I don't know to what extent the stress tensor is consistent with that. In a full theory, I wouldn't, you just wouldn't have flat space in that case. So I don't know.
Any particle physicist is working on flat space-time.
Yeah.
I don't think they're doing incorrect physics.
I know, yeah, but I'm trying to think is what do you do then with